Hello to everyone. In this video we are going to be treating the topic complex transformations. It is a topic that was introduced into the advanced level syllabus of further mathematics since the year 2019, and since that year it has been coming consistently. It came in 2019, it came in 2020, and it came in 2021. So let's get started. Complex transformations, from the name, it's simply transformations that occur in the complex plane. So what is a transformation? First of all, transformation simply means change. So if something undergoes a transformation, it means it is changing. Now there are four different ways for something to change or for something to undergo a transformation. The first way is by turning it. Secondly is by flipping. Thirdly is by sliding, and fourth is by resizing. Now if I am turning something, let's refer to it as an object. It can be a point, it can be a line, it can be a solid figure. If I am turning that object, it simply means I am rotating it. If I am flipping it, it means I am reflecting it. If I am sliding, it means I am either moving it to the left or to the right, or I am moving it forward, or I am moving it backward. If I am resizing it, it means I am either enlarging it or I am reducing it with respect to the original size. Now generally there are four types of complex transformations. We have translations, homothety, rotations, and similitudes. Before we get started, we are going to look at some keywords that we are going to be using in this topic. The first and most important is the invariant point. What is the invariant point? It's simply a point that is being mapped onto itself. So we can see that the image of this point always remains the same as the point. Now the next keyword is the affix. This affix is always referred to as the affix of a complex number. So the affix of a complex number is simply a point representation of that complex number. For example, if we have a complex number z is equal to x plus iy, where x and y are real numbers, then its affix is a point xy. Now let's see detailing what transformations in a complex plane is all about. Now let's consider 2 points, a and b, specifically two complex numbers a and b, whose affixes are za and zb respectively. Now under a certain transformation f, the image of the complex number a is a prime and the affix is za prime. The same thing happens to b. Now generally in the complex plane, all transformations are being represented in this form. Here our transformation is f, so it's transforming the point z to the point z prime. So the transformation is going to be represented in this form. We are going to see what a and b are. With respect to our statement, the transformation transforms the point a to the point a prime. It means that f of a is equal to a prime. So with respect to this general representation, we are going to have this representation for the transformation of the point a to the point a prime. Similarly, the same thing happens to b, and we have this result. Now let's look at what a and b are. Our a and b are complex numbers, and a is different from 0, because if a is equal to 0, then we just have z prime is equal to b, so no point is being transformed actually. Alright, now let's see how we can find the invariant point of any transformation. We can let the affix of that invariant point, which is I, to be z1. Now since we said that the invariant point remains unchanged, it simply means that f of z1 is equal to z1, sorry, zi. But what is zi, or what is f of zi? It is simply zi prime. So replacing in here, we are going to replace z prime with zi, and we are going to replace z with zi. So from there we heal this. Now we look for z1, sorry, zi, which is going to be b divided by 1 minus a. B and a are complex number, remember, but now we need to restrict something. A should be different from 0 as per the domain of definition of my invariant point. Because if, sorry, a should be different from 1, because if a is equal to 1, then we have something here. This is just going to give us something that is undefined, meaning that there is no invariant point. The invariant point is very, very big, so we don't consider it. Alright, now let's try to distinguish these various types of complex transformations. We begin with the rotations. Generally, a rotation is represented in this form, meaning I am transforming a point A to a point A prime about a center omega with an angle of rotation alpha. We are going to characterize this after we see how to express z prime in terms of z. Now let's just choose an arbitrary point. Let's say z, a complex number which is being transformed to the point z prime, and the transformation is said to be a rotation. Now it means that it is going to respect this form, or it is going to satisfy this equation. Now we begin to flip things. If you add omega on both sides of the equation, you are going to get this equation. Nextly, we can expand this and we are going to get this, and now we can factor out omega and we have e to the I alpha z plus omega into 1 minus e raised to the power I alpha. That's z prime. That's the expression of z prime. Now let's look at its characteristics. Remember, we have all transformations represented in the form z prime is equal to az plus b. So if we compare it with this form, we are simply going to say that our a is simply e raised to the power I alpha, and then our b is simply omega into 1 minus e raised to the power alpha, I alpha, sorry. Okay, so characteristics of this rotation. This transformation is a rotation of center omega, that's the affix of the center. The scale factor k is equal to the magnitude of the complex number a, and it is always equal to 1 actually. So it is always equal to 1 for a rotation. So for a rotation, the magnitude of my complex number a is always equal to 1. Nextly, my angle of rotation is the angle alpha. Alright, so that is it for that transformation, which is a rotation. The center omega is the invariant point. So for all these transformations with center, their center is always their invariant point, meaning that the center does not change after passing through the transformation. Next, we look at translations. What a translation is. If t represents it with the beginning of its letter, if t is a translation, then a is equal to 1, meaning that this my a here is equal to 1, my complex number a here is equal to 1, provided it is a translation. So if a is equal to 1, then automatically my transformation, this becomes a translation. Alright, so it means that we are going to have t, which is a translation, to be z prime is equal to z plus b, because our a is equal to 1. Now with that said, we can characterize it as a translation with translation vector u, whose affix is b. So my translation vector is u, and the affix of that translation vector is my complex number b. Okay, let's look at some examples how this is actually indicated. So we have our xy plane. Now if you have a circle named C and it undergoes a translation, it simply means that we have something like this. It moves from this to this. Nothing changes. The C remains the same, but it has moved from this position right up to this position, meaning it has moved a certain distance to the right and a certain distance vertically. So we can say, you can see move it from this point to this point, and we move it vertically upward. So from there, the x coordinate of my affix is simply the horizontal distance that it has moved. In this case, it is in the positive direction, so it is going to be positive. Now the y coordinate of the affix is going to be the vertical distance it has moved. Since it is moving in the positive y direction, then it's going to be positive. If it was moving downwards, then it's going to be negative. Let's see another example. We have our xy plane. Now we have a triangle T. You see it is being transformed to this other triangle, meaning it has moved a certain distance vertically downward and then horizontally to the right. So that's simply what we call a translation, and from there we can determine what the translation vector is. Now let's look at this mathematically. Now z prime equal to z plus b. It means that, let's just say my z is a complex number x plus iy, so the point is going to be xy. Now my z prime should be x prime plus iy prime, so its point should be represented as x prime y prime. Now my translation vector b has affix my translation vector u with affix b has this point, is represented as this point b1 b2. So from there we can equate corresponding entries excuse me, and we are going to see that x prime is equal to x plus b1 and y prime is equal to y plus b2. Remember, our point b, our affix b, or the point b1 b2 is simply the translation vector. So that is basically it about translations. So for translations, we are simply sliding. So we saw sliding, moving to the left, to the right, upward or backward, that is sliding. Now for rotations, it means we are rotating or we are turning. So we can see how now those forms are relating with it in the complex plane. Okay, let's proceed to what a homothety is. If H is a homothety, it means that it is represented in this form: z prime minus omega is equal to k into z minus omega. So I am transforming the point z to the point z prime, and the transformation is said to be a homothety about a center which is omega. K is called the scale factor. We are going to see this geometrically, and my k is different from 1, because if k is equal to 1, it simply means that I have not changed that object actually. So I have simply reflected the object, provided that k is equal to 1. The scale factor is how large or how you enlarged, the factor to which you enlarged or the factor to which you reduced. But if it is equal to 1, it means I have not done anything. So you just see z prime minus omega will be equal to z minus omega. So z prime will be equal to z. So the image will be equal to the point. So that's simply a reflection. I think physics students can understand better. Okay, so this means that here is supposed to be h and not f. So rearranging, we can multiply all through by k. We have z prime to be kz minus k omega, then we add omega on both sides. So simply we express it in this form. So comparing with our general form of what the general representation of a transformation is, we are going to get this, that a is equal to k and b is equal to omega into 1 minus k. Let's see how to characterize this homothety. This transformation will simply be a homothety of center omega, the scale factor k. The center is definitely the invariant point, as we saw. So every transformation that has a center, every complex transformation with a center, that center is simply the invariant point. So to find the center, you simply find the invariant point and you're done. So mathematically, what are we saying? We are saying that if we have a point A that is being transformed to the point A prime under a homothetic, which is a homothetic transformation with scale factor k about a center omega, it simply means that the distance from the center of the transformation right up to the image is a multiple, which is k, times the distance from the center of the transformation right up to the point itself. So if this k is equal to 1, it simply means that what? That the distance between the image and the center of transformation is the same as the distance between the image and the point. So we are going to be talking about a reflection. So for k equal to 1, we are talking about a reflection and not a homothety again, because a homothety is simply either an enlargement or a reduction. But if it is kept the same, then it is a reflection. Nothing has changed. Like I said, physics students are going to understand this concept better. Okay, let's see how we can repeat some examples on what really happens during a homothetic transformation. So that is the general form. Now let's consider an xy plane of this form. Now we have this triangle which is being transformed to this triangle. You see, it is an enlargement, definitely. Now let's see another example. We see, consider our very xy plane. We have this square is being transformed to this square. It is a reduction. So this is an enlargement and this is a reduction. And for an enlargement, our k, our scale factor, is always greater than 1. And for a reduction, our k, which is a scale factor, is always less than 1. I repeat again, if k is equal to 1, it is not a homothetic transformation. It is simply a reflection. Meaning that if k is equal to 1, then this square is going to be reflected about this axis to obtain this square. So we are going to have the same thing. Now let's see how we can, what happens during rotations. So rotation, like we said, it is turning. So we have our xy plane. Now we have this triangle here. We turn the triangle about a certain axis and then we obtain this. So we have rotated it and we have obtained this. So that's simply what rotations are all about. You always be given the center of rotation and the angle of rotation as well. Okay, what is a similitude? Like I said, basically this is going to be based only on direct similitude. So a direct similitude is simply a composition of a rotation and a homothety. It is generally represented in this form. So if you want to compare it to this form, which is a general representation of a transformation, we are going to see that our A will be ke raised to the power I alpha, provided we write this guy in this form. So you can work that out and you see A, the complex number A is going to be represented as this, and the complex number B is going to be represented by this. Now what are the characteristics of this similitude? The center is omega, the scale factor R is equal to the modulus of the complex number A, and it should be different from 1. If it is equal to 1, then we are now talking about a rotation. So a rotation is simply a similitude where the modulus of A is equal to 1. So if this is actually a similitude, then the modulus of the complex number A is different from 1. Okay, the angle of rotation is alpha for sure. The center omega is the invariant point, the same story that we were singing before. So mathematically, what are we saying? We are saying that the distance between, if you consider two points A and B, which have been transformed to two other points, A prime and B prime respectively, with scale factor k, then if the transformation that does it is actually a similitude, then the distance between the two images is a scalar multiple of the distance between the 2 points. That's simply its representation mathematically. Now let's see what actually happens geometrically. So if I consider the point A, the point B, and the point C, and I try to graph out an equilateral triangle, yes, let's say we consider a triangle, but let it be an equilateral triangle. Now I want to transform the point B to the point A, and the center of the transformation should be the point C. Now my angle of rotation is going to be pi ln 3 because it is an equilateral triangle, because I'm doing something like this. B is coming to A, so it rotates about an angle pi ln 3, and the center of the transformation is C, as we have stated. So the scale factor is simply the length, this length, or this length, or this length. They are the same actually, because it is an equilateral triangle, so we can say it is L. Now alpha is my angle of rotation, which is pi ln 3. Now omega is my center and its affix is ZC. Now B is the point that I am transforming with affix ZB, and then B prime is the image, which is definitely the point A, so the affix is ZA. So since it is a similarity transformation or a similitude, we are going to represent it in this form: ZA minus ZC. Remember, our ZA is simply actually B prime, but since it is the image, is ZA. Now omega is the center, in this case it is ZC, is equal to this our scale factor k times e raised to the power I pi on 3 our angle of rotation into ZB, which is the point I'm transforming, minus the center ZC. So that is basically what it is. Now, what about showing that S is actually a similitude? It is very easy to do that. If I am transforming a point A to a point A prime, and I am transforming a point B to a point B prime, and these points are on the complex plane, that is, these points satisfy, actually they satisfy the similitude, because S of A equal to A prime means that A and A prime satisfy. S of B equal to B prime means that B and B prime satisfy. Simply, this is what we are supposed to show. The distance between the images is equal to K times the distance between the objects themselves as defined mathematically. So that is basically it about complex transformations. We have seen rotations, we have seen translations, we have seen homothety, and we have seen similitude. So for what is required in the advanced level, this is basically what you need to know about transformations in a complex plane. Now in the next video, I am going to do tutorials on them, that is solving of the past GCSE equations, and then I'm going to give some tutorial assignments that you can solve and you submit to my email address. If you love the video, please like the video, share the video to your friends so that they can benefit and understand this topic very well. If you have any question, you can comment on the comment section. I am going to include the past question papers in the description below, so that if you need those questions on similitudes, that is similarity transformations, you can download them for free. Thank you for your time and see you later.